share a problem that I found at the online encyclopedia of integer sequences. This was posed back in 2012 by an Omar E. Pohl, I think. I don't know if that's an abbreviation. But this is a famous online digital integer sequencing site. And the type of integers we're interested in right here are the products of two distinct primes. So let's just list a few of them. And this is the actual integer sequence that this problem applies to. 2 times 3 is 6. Those are the first two distinct primes. 2 times 5 is 10. 2 times 7 is 14. Just a little bit of examples here. And now we have to write down 15 since that's 3 times 5. Okay? And so it goes. I'll put the customary ellipse here. But again, 2 times 3. Again, product of two distinct primes. This is 2 times 3. This is 2 times 5. This is 2 times 7. This is 3 times 5. And it goes on and on and on. And this is what they mean by integer sequences that are recorded at this famous website. All right, anyway, this guy had his question, an open question. I think I solved it. So let's get busy on this. We'll assume that P and Q are distinct primes. And we want to show that the sum of the proper divisors minus this thing called the arithmetic derivative, okay, is always equal to 1. Now, before we do it, this is new to me too. So let's take a look at what we might mean by the arithmetic derivative. And I'll just do an easy one. This D represents arithmetic derivative. You can also write it the number prime if you want to. But this is the definition of the arithmetic derivative, and it's not as hard to work with as you might think. Let's do a concrete example. Let's say D at 45. That you're actually this is not like calculus. This is called the arithmetic derivative. That's the way you turn arithmetic into an adjective, arithmetic. Okay, so this is equal to D of 3 squared, and I'm just writing down the prime factorization. Okay. Now another way to write this, not surprisingly borrowing from the calculus notation, is 45 prime. Now, as far as I know, this has nothing to do with what the notion of derivative in calculus means. You know, the slope of a tangent line at the curve at a particular point. But anyway, let's go ahead and complete this computation. So our x would be 45 here. So you have 45 times. Now notice how this is kind of nice. It's the exponent divided by the prime associated with the exponent is how this thing is defined. There's a more rudimentary definition. This is a consequence of that more rudimentary definition. So what you have right here is 2 over 3. And you see, notice here there's an understood, often superfluous exponent of 1 right here. So you would have 2 over 3 plus 1 over 5 parenthetically here. Now, yeah, let's look at the calculation here. That's equal to 45. 2/3 plus 1 over 5 is the same. 10 over 15 plus 3 over 15. That's 13 over 15. And this is 45 right here. Sorry, 45. So yeah, I'm getting 13 over 15 here. And again, you may want to double check the arithmetic there. I think I got it right. 2 over 3 is the same as 10 over 15. 1 over 5 is the same as 3 over 15. 10 plus 3 is 13. So you have 13 over 15. The 15s cancel. You get 3 times 13 is equal to 39. Okay? So I have no clue what that means. Okay? But this is equal to 45 prime. Fairly interesting. Arithmetic derivative. Okay? Now let's get into what we were trying to prove here. This fella here wanted to show that the sum of the proper divisors of any integer minus the arithmetic derivative is always equal to 1. Okay, so let's get busy on that. And again, this is all fairly routine stuff right here. What I did here, this is the famous finite series sum right here. And you could just immediately go to P plus 1 over Q plus 1 because the sum of the divisors of any prime is certainly 1 plus P, which is P plus 1. So you can go right to this line here, replace N with PQ, all right, and let's carry on with this arithmetic here. So this part right here is PQ. All right, and then what do we have? We have plus P plus Q plus 1. So you can already see this is going to head to 1 pretty quickly. So this is 1 right here. Okay, now we have minus PQ, and I'm just writing everything down. So already you're seeing that this pair of PQs cancel out. Now right here, this PQ just directly cancels, and so you have minus P minus Q. All right, folks? So you see, you can see what cancels here. This PQ cancels, and this minus P and this minus Q cancel with this P plus Q, and so you get equals to 1 QED. So that's the end of the proof, folks, and it wasn't a hard proof, but it was posed at the OEIS website, okay? Now, what that means, folks, again, we're done right now. It is equal to 1, and that's what we were trying to prove, right? Equal to 1 here, okay, equal to 1. But what we also know is that every element in this sequence would have that happen, okay? So let's just go ahead and do that. Let's say for 15, what are the sum of the divisors of 15, proper divisors? That would be 1 plus 3 plus 5, right? And we will leave out 15, right? Okay, because 15 is not a proper divisor of itself, of course. All right, now that's going to be minus this result we just established, which is 15. And again, the exponents of 15 are just 1. The exponents of the primes are just 1, so you can write 1 over 3 plus 1 over 5, right? Okay, but notice what this is. This is just equal to 9 right here, minus, and after you do the arithmetic right here, you'll get 15 in the denominator, 3 plus 5 in the numerator. The 15s will cancel, so you'll have 9 minus 8 equals 1. Oh, it's an 8 there. Oh, I made it look like an 8. Congratulations. All right, so there we go. So and every single number in this sequence enjoys this property. I don't know what it's worth or how it's applied, but this gentleman, Omar E.P.O.L., asked this question at the OEIS site. It's a marvelous site. There's so much stuff there. You'll lose your sight. There's so much to look at, you know. But anyway, all the way back in 2012, this was posed as a question, at least the way I understand it. Okay, and it's a fairly easy proof. I'm not sure if he already knew it. I don't know if these are maybe what he meant is, are there other types where you would have this being equal to 1? These are certainly true, but are these the only ones? That's maybe a deeper, harder question, but we've at least proved that these type of integers, products of 2 primes, sometimes called semi-primes, sometimes called square free, have this property that's related to this notion of a derivative. All right, that's all. Thanks for viewing.